if a cell doesn't burn energy, like we said earlier, the ATP is very high. The ATP synthase doesn't turn. The membrane potential is really high. The electrons have nowhere to flow. There's too much resistance. So that resistance then propagates like it would in an electrical circuit, and then it propagates upwards. And then the resistance then manifests at the level of the cell's surface, the plasma membrane, by removing the transporters for glucose, which effectively increases resistance, right?
Right.
So that's there's this beautiful paper from 2009. The title was "Insulin Resistance is an Antioxidant Defense Mechanism." That's in PNAS, right? And they were saying the reactive oxygen species that mitochondria spit out when there's excess energy resistance. They didn't use those terms, but they did the same kind of experiments I mentioned earlier, where you feed mitochondria lots of electrons, but you don't let them respire, you don't let them produce ATP, spit out tons of reactive oxygen species, and then they showed how this then propagates to the plasma membrane, and then the cell becomes insulin resistant. So the pathology of insulin resistance is, I think, starts in the mitochondria and, or somewhere along, right, where the flow of electrons is not high enough to support the pressure. So it's a pressure to flow issue, and the core driver of pathogenesis is the system is overloaded, right?
Right. The cell's saying, I can't handle all these electrons from all this glucose or whatever, so stop giving me so much.
Exactly. So so the insulin resistance really is an issue of energy, or is the manifestation of a deeper seated energy resistance.
So then from a therapeutic standpoint, you'd want to focus your attention on fixing the mitochondrial problem rather than trying to...
There's no mitochondrial problem.
It's like a selective pressure problem of the flow of electrons.
Yeah, the flow problem, as opposed to trying to undo the insulin resistance.
And I've heard, a couple clinicians who were reflecting on the use of insulin therapy in diabetes, because the standard of care nowadays, which is from a molecular perspective and how you started that question, there's an issue at the cell surface, like insulin signaling is not happening. Let's restore it. Let's fix this, right? And then one approach is to say, the cells are insulin or resistant to the effect of insulin. So let's give more insulin. Like that is the mindset that biomedicine is using to counter that problem. What this does at the cell level, you have the cell here, it says, oh, like the pressure of glucose, of electrons is so high, let me protect myself. And then the cell kind of finds some respite probably in like becoming insulin resistant. And then there's like 10 times the amount of insulin that comes in, and then it's overloaded. And then you start to damage your mitochondria, right? And there's some notion in diabetes management that giving insulin is useful at decreasing blood glucose. So HbA1c goes down, but now peripheral organs starts to suffer. And there might be more, nerve damage, like neuropathy, and more some of the other damage in some tissues that are, insulin sensitive, because you're forcing glucose into cells effectively that are trying to protect themselves. So the energy resistance principal approach to disease management is twofold. Either you increase flex, right? How do you increase flex? You increase flex by moving. If you contract the muscles, that's going to increase the flux. You're going to breathe harder. So anything that kind of makes you breathe harder should be good to increase flux in the system. Or the other approach is to decrease the numerator, the energy potential, and you do that by eating less sugar.
The source of the energy.
Yeah, that we know insulin resistance in I don't know what the percentage is.